This is a video on logistic differential equations, and we will be first looking at an exponential differential equation just to remind us of that type of function. So in exponential growth, that's a function that grows unlimited, with unlimited growth, or grows without bound, and it is written as a differential equation as the rate of change of y is proportional to the value of y. And so what happens with this is if the y value is small, the rate of growth is small, and when the y value is large, the rate of growth is increasing. And so as the y value increases, the growth rate increases, and so the slope just gets steeper and steeper and steeper. The solution to the differential equation is this, and we are going to see where that comes from by solving the differential equation. Recall that c is the initial value, and when k is positive, we get a growth situation, and if k is negative, we get a decay situation. So in solving this differential equation, we first separate the variables and get that 1 over y dy is equal to k dt, and then the integral of both sides will lead us to the natural log of the absolute value of y, which is equal to kt plus some constant c. Then to isolate the y, I'll write that the absolute value of y is equal to e to the kt plus c, and the absolute value of y, we can think of that as e to the c is equal to e to the kt. Now, to get the absolute values off, I would put a plus or minus on this side, and recall that the whole point of this c is to represent any arbitrary constant, and so e to the c is just a constant also, and the plus or minus is just a constant, and so we can say that this is c e to the kt to get this solution. And the graph of that function is when k is positive, you get this exponential growth situation with a horizontal asymptote of y equals 0, and then the graph is growing without bound, and the slope is constantly, as the y values increase, the slope is also increasing. Now, in a differential equation, the growth reaches an upper limit for which the growth cannot pass. So the upper limit L is called the carrying capacity, which is the maximum population that can be sustained or supported as time increases. So there is a horizontal asymptote here, and there is also a horizontal asymptote at y equals 0. So this differential equation, if you solve it using similar steps to this process, will get you to this solution. Now, the steps to get from this equation to this equation are long, and I don't think it's the best use of time in our video, though I did work it out and thought about showing it to you. So if you wanted to pause the video and work through this solution, you could, but I think it would take me about 20 minutes on a video and would be difficult to follow. You are not required to be able to solve this differential equation. You are just expected to know some properties about this differential equation and this solution and this graph. So we're going to proceed from there without working out the details of the solution between these two. One thing that is definitely required that you know is that the limit of this function as time goes to infinity is L over 1 plus b e to the negative kt. That's not super difficult to figure out, because as time increases, then e to the negative kt, if the time is getting infinitely large, then e to the negative kt is getting small, because e to a negative power is approaching 0. So this will become L over 1 plus 0, or just L. So that's why this function has L as its upper bound, because the limit as time approaches infinity is L. Then the other bits of this equation, the k affects the growth rate. K is the growth rate. And the b, it's not directly the y-intercept, but it affects the y-intercept. And then thought we'd take just a second to look at a Desmos graph of this differential equation. And I put in sliders for each of these so that you could see what happens when, say, the L value, the carrying capacity, changes. That should be impacting the upper limit of the graph. And so you can see that if I bring this down to 5, that the horizontal asymptote is now 5. And the k value affects how steep the graph is. So if the k value gets smaller, then it takes longer to get to the carrying capacity. And it doesn't impact the y-intercept there, but this variable b affects the y-intercept as it changes. Let's change this and see what happens here. There we go. So the b value is not directly equal to the y-intercept, but as the b value changes, it changes kind of the starting value of the graph. All right, so what we're going to do next is an example of how you'll be expected to know, what you'll be expected to know about this. One other thing is that this inflection point right here is always equal to some value of time that you'll possibly need to solve for, but it's always equal to half of the carrying capacity. So there's some symmetry to this graph such that as the slope is increasing, and then the slope is still positive, but now the slope is decreasing, that point where it changes from increasing at an increasing rate to increasing at a decreasing rate is always exactly at half of L. And the AP test loves that question of having you know, just to demonstrate that you know that that occurs there. All right, so we are going to look at a specific example. This is example 10 from your textbook with one additional question added to it there. First thing is to write a model for the elk population at time t, and the situation is a state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104, and the commission believes that the environment can support no more than 4,000 elk. The growth rate is given by the elk. The growth rate of the elk population is dp dt is equal to kp times 1 minus p over 4,000, where the p values are between 40 and 4,000. So the first step is to write a model for the elk population in terms of t. Now, you don't actually have to go solve the differential equation. You just get to take this dp dt equaling k, which we don't know, and p is the independent variable, like the y, dy dt, now it's dp dt, and the 1 minus p over 4,000 And notice that the 4,000 is the L variable. So when you go to write the P of t function using this solution, y equals L over this business, we know what L is. So then we can say that the solution to this differential equation is 4,000 over 1 plus b e to the negative kt. You're not expected to have to memorize this, but for this homework set, we are going to just get used to using this formula so you can have it written down and look back at your notes for it. It'll be fine. So because they told us that there were 40 elk released initially, then we know that the population at time 0 is 40. And we also know that the population at time 5 is 104. So those two population and time values will allow us to solve for the two remaining variables in this. So we can find that when p of 0 is equal to 40, that we get 4,000 over 1 plus b e to the negative k times 0 is equal to 40. And so this becomes 4,000 over 1 plus b e to the 0, which is just 1, which is 4,000 over 1 plus b is equal to 40. Then to solve this for b, I'm going to say that it's 40 times 1 plus b, and divide both sides by 40, so I get that 100 is equal to 1 plus b, or that b equals 99. And so now I know the b value, I can come up here and solve this equation with 1 plus 99 e to the, I still don't know k, but now I know that t is 5, and when t is 5, I know that the population is 104, and then I can solve this equation for k. So I will multiply both sides by this denominator. 104 times 1 plus 99 e to the negative 5k. And then if you divide both sides by 104, you get 500 over 13. 4,000 over 104 will simplify to that. We could get a decimal approximation and write it there. That would be fine. Then I would subtract 1 and divide by 99. To equal e to the negative 5k. And then take the natural log of both sides. And eventually you would just stop and get this all on your calculator, but then this will be negative 5k times the natural log of e. Natural log of e is just 1, so then you would take this quantity and divide by negative 5, and you will get that k is equal to 0.194. And so then we have the differential equation. We have part A done. Write a model for the elk population in terms of t, and that comes out to be P of t is equal to 4,000 over 1 plus 99 e to the negative 0.194 t. All right, then part B says to graph the slope field and the differential equation and the solution that passes through the point 0, 40. I didn't think that would be it's hard to graph a slope field on your own and to do this on a calculator or whatnot. I just put the solution to that here. So we can skip part B and just have that there. Then, so we've done part A. Then it says to use the model to estimate the elk population at time 15. And so for part B, we would just find P of 15 and take this equation and substitute in 15 to get the answer to it. And somehow I don't have that handy, so you'll need to fill that in yourself. I'm not going to take the time to do it right now. D says to find the limit, or this was C. D says to find the limit as t approaches infinity of 4,000 over 1 plus 99 e to the negative 1.94 t. And you should be able to quickly realize that the answer to this is just going to be 4,000, the carrying capacity. You could think it through and know that if the time value is growing, that this quantity is getting close to 0, and so you'll get 4,000 over 1 plus 0. But it would be great if you just knew that the carrying capacity is the answer to this limit. And then the last question is, what is the population when the elk population is growing most rapidly? So the elk population is growing most rapidly at the point of inflection. And we talked about just a few minutes ago how that point of inflection is always at half of the carrying capacity. So if the carrying capacity is 4,000, then the p-value of the point of inflection will be half of 4,000. You could find and solve for that value if you took the derivative of the differential equation, if you got the second derivative and set it equal to 0. And we will look at that more in depth in our next lesson. But for now, it is just helpful to know that the point of inflection is always at half of the carrying capacity. Notice that this asks for what the population is when the elk population is growing most rapidly. So the answer to the question is P equals 2,000. The population of elk is growing fastest when the population is 2,000. Now normally you're asked to find the time value in this situation, but I just thought that it was enough in this video to just find the population. But what would you do if you needed to find the value, the time value at this moment? You would just take your P of t function and set it equal to 2,000 and then solve for the time value. So you know how to do that. It would be similar to the work that we just did in this example, and I didn't think it was necessary here. But I did want you to think about the fact that this inflection point is always at half of the carrying capacity.